Example 7.6. A. Describe the behavior of the capacitor's voltage. Does it charge up or discharge? B. Calculate and plot the voltage of the capacitor. So what we want to do here is that we want to interpret the behavior of the capacitive voltage for t equal to 0 minus and t equal to infinity. So at t equal to 0 minus, look what you're seeing here. There is no exponential source because it hasn't turned on. There is a voltage source and there is a dependent source. So when I look at the circuit, it looks something like this. So I have my 12 ohm, I have my 2ix, and I see that ix is in that direction, which tells me, gives me a polarity like that. Then there is no source, exponential source, but then the capacitor has now reached steady state. So I know that this guy is Vc of 0 minus. And I have a resistor here, and I have my source right here. So the way I look at it, that there are two sources that are feeding the capacitor. There's the 2ix, and then there's the 38.5 volt source. So I have two sources increasing Vc of 0 minus. Now, when the switch is thrown and I allow this to go to infinity, note that the switch opens up, so there's no voltage source. And as a consequence, I of x goes to 0, so that current source becomes an open. So when I look at t equal to infinity, I'm seeing that I have a resistor and I have 0 sources. And so the current source is now an open, and then the capacitor is an open, and so this guy gives me plus minus Vc of infinity here. Clearly that guy has to go to 0 because there's nothing there to supply it. So here, so that there are no sources at t equal to infinity. So what this tells me right away here is that we expect a discharging capacitor because Vc of 0 minus is going to be greater than Vc at infinity. So now we're going to go through our process here. So let's go through our process. So here I go. So this is step 1. Step 1, we need to derive the first order equation at t equal to 0 plus. I'm going to use a 2-step process that one I need connects, let's see, that connects Vc and Ic together, And typically we're talking about either using KVL/KCL combinations or just one of them. And I need to write a DC equation for IX where it has to be a function of VC or IC. So let's do that. So if I look at my circuit here, you could see here is that I don't have the 38.5 and 3 ohm resistor. So my circuit looks like this. So I have a resistor here. That's going to be my 12 ohm. Then I have my dependent source, which is 2IX. And you're seeing here is that this is IX right here. So IX is the current through the 12 ohm resistor. And now I have my dependence, my exponential source that has turned on. So this is minus plus. And then I go to my capacitor here. So remember, this source is 8e to the minus 5t. So what I'm seeing here is that I'm seeing this. I have a voltage VC in this direction. And clearly I have a current IC in that direction. So now what I'm going to do here is that I have to determine my IC, my DC, and I have to connect VC and IC. So here I go. So the first thing that I'm going to do here is that you could see here that I need to connect IC and VC here. So I think the first thing that I'm going to do is I'm actually going to go after the DC first. So I'm going to go for my DC first. Okay, so I'm going to write the DC equation for IX. Now, what you want to do here is that look at this green node right here. I'm going to apply KCL. The reason why I'm going to apply KCL is look at that. I got IX plus 2IX has to equal IC. So I'm going to apply KCL at the green node. And you could see that the currents coming in has to equal the current coming out. So I'm going to get IC. It's going to equal to IX plus 2IX, which is, of course, 3IX. So that tells me I'm going to write IX as 1/3 of IC. Now, if I have IC, but remember IC, and I did not write this in, that's the capacitance right there. IC is equal to what? It's equal to C dV, 1/C dV dt. So this is really 1/3 times 1/36 times dV dt. So I can now replace IX with this term right here. Okay, so now let's go put that in now. So now I have that. So this is my condition for IX. So here's my DC. So now what I want to do is that I need to connect IX to VC now, because note, IX is connected to IC, but now I've converted it all to V. So what I'm going to do here is that I'm going to apply KVL around the outside loop of the circuit. So if you look at that, look what happens. I'm going to start at the capacitor. If I start at the capacitor, I'm going to get VC, and I'm going clockwise. Then that means I come around, I'm going to get the voltage V12. And of course, I come back and you see I get a minus sign. So I'm going to get minus 8e to the minus 5t, and that's equal to 0. Now let's clean this up. So if I clean this up, look what I'm going to do now. This tells me here is that V12 plus VC. Now look at V12. It's going to be 12IX plus VC, but I know what IX is over here. That's the DC. So this is going to be 12 times 3 times 36 times dVC dt plus VC. And if I continue to move in this direction here, I'm going to get what? 12 into 36, that's going to give me a 3. So therefore, this really gives me 1/9 dV dt plus VC. And then finally, I'm going to get 8e to the minus 5t. Now what I'm going to do here is I'm going to put this into proper form. So if I put this into proper form, I now have an equation that reads dV dt plus 9v equals 72 e to the minus 5t. So this is my first order equation right here. So now what I want to do here is that I want to check this. I want to check this differential equation for VC at infinity, which of course is going to be a constant, but that constant I label as B usually. So let's look at a mathematical check. So if I look at a mathematical check, what do I get? My mathematical check essentially says I'm going to write dB dt plus 9b has to equal 72 e to the minus infinity, which is of course 0. So this immediately tells me that B, which is VC at infinity, is 0. That's what the mathematical one. But what does the circuit check tell us here? So now if I look at the circuit check, we saw that this was the circuit over here. We have it right here, right? And when we look at the circuit, we see that this guy is definitely has no source in it. So when I look at the circuit, it really looks like this here. The source is now gone, the dependent, and then now I have this, and you could see here that this guy is then VC of infinity, and you could clearly see with no source, clearly this guy has to equal 0. So what we can see here is that both of these agree. The circuit check and the mathematical check agree. So both checks agree. So I'm going to say that we're good right there. So now that I have that, I'm going to go to step 2. Here we go. Step 2. I want to determine the general response and calculate the force and response constant B. So now here we go. From the first order equation, we see here is that we have dv dt plus 9vc, and this is equal to 72 e to the minus 5t. So what I'm going to do from here is that you could see here, I'm going to pick off 1 over tau. And then you could see on this side here, this is my effective source. So then my general response implies that my forcing response has to be the exact same shape. So then I'm going to have my general response. So my general response then has to be, of course, Vc of t, which is going to be what? V natural plus V forcing. And this has to be, my natural is going to be AE. Now look at that. 1 over tau is 9. So then this becomes minus 9t. And then I have my force response, which is going to be B times e to the 5t. And this is going to be Vc of t. So now I have my general response here. So the first thing that I got to do here is that I have to go determine the forcing constant B. So here we go. So now what I'm going to do is that I'm going to determine the force response constant B. Now the way I do this here is that I have to substitute the force response into the differential equation. So that means when I look at my force response, it has to look like this. But my force response has to be of the order of B e to the minus 5t, as we just showed here. So if I plug this in, look what I'm going to get. I'm going to take the derivative of this guy. So I'm going to get minus 5b e to the minus 5t. And then I'm going to get 9b e to the minus 5t. And that has to equal 72 e to the minus 5t. So immediately we can come in here and you can see that I have a cancellation of all of these. So then I'm going to get what? 72 divided by 4 is then going to be b. So then this tells me here that b is then going to be 72 divided by 4, which is the same as 18. And I now have my force response right here. So now if I put things together, the general response now looks as Vc of t, then this will be A e to the minus 9t plus 18 e to the minus 5t. So now my job here, as you can see here, is that I have to determine the constant A. So here we go. So I'm going to move this up here. And what we're seeing here is that we're now on step 3. Step 3, we need to determine the initial voltage of the capacitor at 0 minus and calculate the natural response constant A. So I need the circuit at t equal to 0. So at t equal to 0 minus, here's what we have for our circuit. So here's our circuit right here. And note that at t equal to 0 minus, there is no exponential source. So that means here that my source now looks something like this. My circuit looks something like this. So I'm going to have a resistor. Then I have my dependent source. So here's my 12 ohm. We clearly see here that this guy is IX. This guy is 2IX. The capacitor is now in open. And then I have this resistor and source like this. And so this guy right here is now VC of 0 minus. So the easiest thing to do to try to get a sense of how the current is flowing is that I'm going to do a source transformation right here. So if I do a source transformation, note then that 38.5 divided by 3 gives me 12.8 amps. So now I have a current source that's in parallel to that 2ix. So I'm now going to add this new current source of 12.8 plus 2ix because they're pointed in the same direction. So now I'm going to redraw the circuit. So look at that. I have two sources. One is 12.8 plus 2ix. And then here's my dependent current source right here. So that's adding those two current sources. Now, the thing that you want to pay attention to is that one, I have this resistor, the 12 ohm resistor, and then I have the 3 ohm resistor, and then I have my open. But note that open is in parallel to the 3 ohm as well as the 12 ohm. So this turns out to be VC of 0 minus, which is the same as V3 of 0 minus. So now I have IX flowing up like this. So if I look at the circuit a little bit more careful, this is kind of what I'm seeing here. I clearly see that this node is my ground. And then the top node is VC. Now, the thing about it here is that I really don't need to talk about the nodes or anything because this is a parallel circuit. So because this is a parallel circuit, I need to calculate IX first and then apply Ohm's law. To get VC of 0 minus. So let's do that. So the first thing I'm going to do is that I'm going to determine the DC IX term. Okay, so I'm going to use, because this is parallel, so I have a parallel circuit, so that means here I'm going to apply CDR. So if I apply CDR, look at that. I want the current of the 12 ohm resistor. So if I want the current of the 12 ohm resistor, it goes like this. So I12 is then going to be 12 plus 3 divided into 3 because it's the opposite resistance times the source, which will be 12.8 plus 2ix. But this is also equal to ix. So note I have one equation and one unknown. So now what I'm going to do here is that I'm going to solve for ix. And if I solve for ix, I get that ix is now 4.27 amps. So now I have ix. So now that I have ix, what you're seeing here is that, look at the circuit here. We already said that these are parallel elements. And because they're parallel elements, VC is the same as 12ix. So I don't even have to look at that 3 ohm resistor because they're all parallel. So now what I'm going to look at is that I'm going to look at Ohm's law to compute VC of 0 minus. So that means here is that VC of 0 minus, now look at the polarity. The polarity of the 12 ohm and the 3 ohm are opposite. So I have a negative sign of 12ix, but that's just going to be what? 12 times 4.27 gives me minus 51.3 volts for VC of 0 minus. Okay. So now that I have that, the next thing I need to do here is that I need to apply this initial condition to calculate the natural response constant A. So then I have VC of 0 plus must equal minus 51.3. But remember, look at my equation. My equation is A times e to the 0 plus 18 e to the 0. So then I'm going to get A times e to the 0 plus 18 times e to the 0. Now all I have to do is then solve for A. So if I bring the 18 to the other side, that means here is that A is now equal to minus 69.3 volts. So now I have all my constants that I need. So what do I know? So the complete response is this now. So it's got to be VC of t. That has to be minus 69.3 e to the minus 9t plus 18 e to the minus 5t. So here's my solution right here. So what this tells me here is that because this is a capacitor, there are no discontinuities. When a switch is thrown. So now what I'm going to do here is that I'm going to plot this guy, and it looks like this. So everything is negative. So I'm going to say that I'm going to look at my curve like this, and we know that this is VC of t. And here's what, oh, that's too low or too high. Let's bring it down here. And this is VC of t. So VC of 0, VC 0 minus is negative 51.3. So you could imagine that this guy right here is negative 51. So you can see here is that right here, for a long, long time, I have a constant value right here. In other words, this is VC of 0 must be negative 51.3 volts. But you could see here is that there's no force response. This thing has to go to 0. So then if I look at this, this guy has to go from here to there. So when I look at this thing, you could now see here is that about right here, I'm going to call that 5 tau, and this is where it fully charges up. And by the way, at VC of infinity, you can see that this is 0 volts. So if I look at my time constant is 9. So the time to fully charge is 5 tau, but this is the same as 5 over 9, which will then be 0.56 seconds. So this is 0.56 seconds. So it discharges a little over half a second.